Look at our planet, floating serenely in the blackness of space. It looks peaceful, doesn't it? But what this picture does not show is the constant, invisible war being waged just outside our doorstep. We are living in a safe haven, a fragile bubble protected from a storm of radiation that fills the entire cosmos. This is not a metaphorical storm, it is a very real, physical one, made up of tiny, invisible particles traveling at almost the speed of light. They come from our sun during violent solar outbursts, and from the distant deaths of massive stars in the form of cosmic rays. For us on the surface, this cosmic war is just a distant rumor. Our planet's magnetic field and thick atmosphere act as a perfect shield, deflecting and absorbing these harmful particles. They are the reason we can safely look up at the sky. But the moment we leave this protective bubble, we step directly into the line of fire. This is the first, and perhaps greatest, challenge of human space exploration, the hidden danger of space radiation. It is an enemy we cannot see, cannot feel, and cannot hear, but it has the power to stop our dreams of reaching other worlds. In this video, we will uncover what this radiation is, why it is so dangerous for both humans and machines, and the sobering realities that space agencies like NASA are grappling with as we plan missions to the Moon and Mars. So, what exactly is this space radiation? Imagine trillions upon trillions of tiny, invisible bullets, each carrying immense energy, flying in all directions through space. These bullets are atomic particles. The most common types come from two main sources. First, from our sun, we get solar particle events, massive eruptions like solar flares and coronal mass ejections that blast billions of tons of protons and other particles across the solar system. Think of it as the sun having a temper tantrum. These solar storms are intense but often short-lived. The second, and more persistent, sources from outside our solar system. These are galactic cosmic rays. These are not rays of light, but rather the nuclei of atoms like iron, silicon, and carbon that have been accelerated to incredible speeds by the explosive forces of supernovae and black holes. Because they are so heavy and so fast, they pack a much more powerful punch than solar radiation. Unlike solar particles, galactic cosmic rays are always there, a steady drizzle of high-energy atomic shrapnel raining down on everything in space. They are so energetic that they can tear right through solid metal, plastic, and human tissue. This constant, background shower of atomic nuclei is the baseline danger for any space traveler. Understanding this enemy is the first step in figuring out how to survive it. Now, let us talk about what happens when these invisible bullets hit a human body. On Earth, when we think of radiation, we might think of X-rays or nuclear accidents. But space radiation is different. It is more destructive. When these high-energy particles, especially the heavy galactic cosmic rays, fly through an astronaut's body, they do not just pass through harmlessly. They act like microscopic cannonballs, smashing directly into our cells. The most critical damage happens to our DNA, the fundamental instruction manual for every cell in our body. The particle can break the DNA strands directly, or it can create a shower of secondary radiation inside the body as it collides with other atoms, causing even more widespread damage. Our cells are amazing at repairing this damage, but the radiation in space is so intense and unusual that the repair mechanisms can be overwhelmed or make mistakes. These mistakes are mutations. Over time, this accumulated damage significantly increases the risk of developing cancer later in life. But the dangers are not just long-term. Astronauts on the International Space Station have reported seeing strange flashes of light even with their eyes closed. This is actually cosmic rays hitting their retinas. More immediate effects can include radiation sickness, weakened immune systems, and, on a long enough journey like a trip to Mars, potential damage to the central nervous system, which could lead to memory loss or reduced cognitive function. The human body simply did not evolve to handle this kind of assault. The danger of space radiation is not limited to human biology. Our technology is just as vulnerable. The sophisticated electronics that power everything from a spacecraft's navigation computer to its life support systems are built on silicon chips. These chips operate using tiny electrical charges. When a high-energy radiation particle slams into a microchip, it can disrupt these charges. This can cause a phenomenon called a single-event effect. There are two main types of these effects. The first is a single-event upset, which is like a digital hiccup. It can cause a memory bit to flip from a 0 to a 1, corrupting data or causing a computer to freeze. This can usually be fixed by resetting the system. The second, more serious type is a single-event latch-up or single-event burnout. This is when the particle creates a short circuit, causing a surge of electricity that can permanently destroy the component. Imagine a single, invisible particle from a distant galaxy traveling for millions of years, only to arrive and instantly fry a critical computer on a spacecraft headed to Mars. This is not science fiction, it is a regular engineering challenge. Shielding electronics is incredibly difficult because the very act of stopping these particles with thick metal can create a secondary shower of even more particles, making the problem worse. Protecting our machines from this invisible barrage is as critical as protecting our astronauts. So, what is the solution? Our first instinct is to build a shield. On Earth, we use lead for radiation protection in hospitals. So, why not just build a spaceship with really thick walls? The problem is that space radiation is fundamentally different from the X-rays or gamma rays we deal with on Earth. Remember those heavy galactic cosmic rays? When these high-energy atomic nuclei slam into a dense shield like lead or thick aluminum, they do not just stop peacefully. They shatter on impact. This collision creates a secondary radiation shower, a burst of even more, smaller, but still highly energetic particles. It is like using a sledgehammer to stop a bullet. You might stop the bullet, but you will create a dangerous cloud of shrapnel in the process. Inside the spacecraft, the astronaut could be exposed to even more radiation than if they had a thinner shield. This is the great shielding paradox. Scientists are exploring new materials, like hydrogen-rich plastics or polyethylene, which are better at disrupting these particles without creating as much secondary radiation. Even water and food supplies can be strategically stored around the crew cabin to act as shielding. But any shield thick enough to be truly effective would be impossibly heavy, making the spacecraft too expensive to launch. There is no perfect, simple solution. We are stuck choosing between inadequate protection and impractical weight. This brings us to the final, sobering question: if space radiation is this dangerous and so hard to stop, can we ever safely explore deep space? This is the challenge that organizations like NASA are working on every day, even if they do not always highlight it in their public announcements. For short trips to the moon, the risk can be managed by carefully timing missions to avoid major solar storms and using spacecraft with enhanced shelter areas. But for a multi-year journey to Mars, the accumulated dose of galactic cosmic rays alone presents a severe, unavoidable health risk. So, what are the possible solutions? Researchers are investigating revolutionary ideas. One concept is to create an artificial magnetic field around the spacecraft, essentially replicating Earth's magnetosphere in miniature to deflect charged particles away. Another idea is the use of pharmaceuticals, radiation pills that could help the body repair DNA damage more effectively. We could also build habitats on the Moon and Mars inside natural radiation shelters, like underground lava tubes. The path forward will not rely on a single miracle solution, but on a combination of strategies: faster spacecraft to reduce travel time, better forecasting of solar weather, advanced materials for shielding, and medical countermeasures. The conversation about space radiation is not meant to stop exploration, but to fuel smarter innovation. Acknowledging this invisible cosmic threat is the first and most crucial step toward overcoming it, and ensuring that humanity's journey to the stars is not a one-way trip.